You're right. Yeah, welcome back to Introduce. This is mathematics. So today I hope to start theoretical part of probability. So probability and statistics. So I have explained the basic fundamental thing of the theoretical part and the application part, how it will be continued up. Right. So let's try to have an idea. Probability is what? Probability is the measure of the likelihood of the occurrence of an event. So mathematically, an event, if you're going to take an event as upper E, so the probability of this event can be denoted by PR inside of parentheses upper E, right? So then the governing sample set is being existed between 0 and 1. Right, it means the probability exists between 0 and 1. Right, okay. It never exceeds 1, it may not be decreased uh, less than 0. Right, okay. So with this idea, let's see. There is a function. This is what? This is the variable. This is sample space. Domain is sample space. I'm gonna pick omega values for the sample space. There are sort of sample space, there may be infinite number of, so this is the variable, right? So with variable, let me denote variable with upper X, right? Okay, keep this in your mind. There are particular meanings of upper X and little x. Give me only a few seconds to change this brightness. I feel like that is not no. Right, okay, that's better. Right, okay. Then this will be connected with induced sample space. Let me call these elements x1, x2. These are corresponding elements, right? Okay, so with this idea, this is sample space, this is variable, and these are connected with induced sample space, right? Okay, so then let me summarize it mathematically, and also I need to let you know that there are basically two types of random variables. Those are called something discrete random variables and also continuous random variables. So based on these two types, we will describe two probability distributions. These are probability distributions, so it's up to those two types. Once we talk about once we base on discrete random variables, we used to call those type of probability distributions discrete, based on discrete random variables. We used to call these type of probability distributions as probability mass functions, PMF, right? And also based on continuous random variables, we used to call them probability density functions, right? Let's see how we can distinguish these things. I'm pretty sorry. Continuous random variables based on these things, so we used to call them probability density function. So right, okay. With this idea, let's try to have an idea with mathematically how to represent these things as a set, how this can be defined with mathematics, right? So probability of random variable, this is the induced sample space inside of this parenthesis, right? So we can say that the same thing can be rewritten using another way. probability of x equals to little x. It doesn't matter whether you are gonna use this one or this one, both these things are having the same meaning, right? And x is an element of real numbers, right? Okay. So for an example, rain, volume of rain. The type is continuous data. That's a continuous variable, because we are not able to measure it with accurately. That cannot be measured. That can never be measured accurately, because it's up to our instrument we are going to use, right? So the accuracy is up to our instruments, right? Okay, so those type of variables can be classified as continuous data. So number of students, we are not able to say 3.5 number of students. Those type of data can be classified under discrete, right? Okay, then you can how we can get the proper idea about how we can distinguish these discrete and continuous data, right? Okay, let me show you some more how can we describe this sample space and induced sample space, right? Let me clean this, right? Okay, upper x equals to little x. This sample space was picked as omega. Omega is an element of sample, right? Sample space. Omega is an element of sample space, really, omega I. So where that can be defined as a function of random variable. You can check it with this relationship, right? I can connect these. We can go furthermore, right? Okay. So that is all what we need to know with the fundamental stage, right? Okay. So once I go furthermore, I want to explain you what are the properties of these probability distributions. Yeah, first of all, I need to make you remember once again there are two types of probability distributions. Based on them, they were defined as probability mass function. So first of all, I'm gonna talk about probability mass function only, right? After that, we can have an idea about probability density functions also, right? So let me explain you what about those properties about on these two distributions. I need to clean this, right? Okay, right. For any x is an element of real number set. This is the probability x is between 0 and 1. This is one of property. This is very compulsory. If you ask to show whether this is a probability function or not, probability distribution or not, this is one of property you need to check, right? Okay. So then the next property related to the probability mass function. I told you that there are two types, right? So I'm talking about probability mass functions, right? In a later session, I will be talking about probability density function, also PDF, right? But here stands for PMF. Always from here. All these ways from 0 to 1. All probability can be denoted with summation of each of every induced sample space. Here, this is going to be equal to 1, right? This should be equal to 1, otherwise we are not able to say between that range. That cannot be defined as a PMF. If any function satisfies these two properties simultaneously, it means that that can be introduced as a probability mass function, right? Okay, thank you. I'll give you some examples once I go through them all. For now, it's enough, right? Okay, thank you for watching.